Change that to 8.2, okay, kids? Change that to 8.2 up here. And 8.2 is titled what, kids? Similarity and Transformations. Now, kids, there's going to be a lot of things that they expect you to have prior knowledge on, and I'm going to be quite honest with you. I'm guessing that some of that prior knowledge has escaped your mind within, it's probably about a year ago that we talked about this, if you had me last year. A lot of you guys were in here last year, weren't you? Okay. So it's probably been a year. Now it escaped your mind a little bit. We're gonna put some things together today to make life pretty easy for you. Is that fair?
Oh, yeah. Sure.
Okay. Guys, what's true about similar figures so far? What do we know about similar figures? Same shape, but the size will differ, right? Okay? So we'll talk about that. Guys, think about two squares. Think about two squares that are different sizes. What's true about all the angles in each square, the big one and the small one? They're all 90 degrees, but how about the lengths then of a big square compared to a small square? Okay, going to be different. So angles are preserved, lengths change. We're going to talk about similarity. What does it mean to be similar and then transform some stuff? Transforming stuff simply means how do you move something? You might slide it, you might rotate it, you might flip it, or the new one from 8.1 is you might, like our eyes, dilate them, make them bigger, change the size, and that's where the similarity part comes in. Okay? So, as 8.2 is titled Similarity and Transformations, I'd like to know, what are we trying to answer here? Now, Frisbee's not here, guys, so someone's going to have to carry the weight today.
Yeah,
Who wants it?
Adam's the most likely. Well, that's it.
Jacob, why don't you do it?
You want it, Bree?
When a figure is translated, reflected, rotated, or dilated in the plane, is the image always similar to the original design?
Okay, so when an image or when a figure is translated, meaning slid, reflected, meaning flipped, rotated, meaning turned, or dilated, change of size, in a flat plane, is that image always similar? We're going to look at that stuff, okay? I think I know the answer. You guys remember this right here?
Oh, rigid motion, yes.
Remember talking about that last year? What did rigid motions mean?
The thing moves without the shape.
It moved, but the size did not change. It was the same. Okay, so remember that. Rigid motions are movements that move a figure, but they will not change the size. Okay? I'm going to underline everything up here that's a rigid movement. Translation means slide, reflect, rotate. Is dilation a rigid motion?
No.
Why not?
Because dilation is a size change.
It's a size change. So these three things that I've circled right up here or underlined it, these are all considered to be what? Rigid motions, okay? So to answer that question, we're going to look at performing some similarity transformations. We're going to describe those similarity transformations, and we're going to also prove that figures are similar today. So this won't be too terrible. But when I say it's not going to be too terrible, you probably start thinking, so it's going to be kind of terrible, right?
No, there's only 3 examples.
It's pretty simple today.
Oh, rotations. I remember that.
All right, kids.
That was so confusing, I think.
We need to remember some things. First of all, similarity transformation. A similarity transformation is a, what's the word? Dilation or a composition of what?
Rigid motion.
Rigid motions and what?
Dilation.
If you are going to have a similarity transformation, you have to change size. And of the 4 transformations described up there in the essential question, the only one of those motions that was going to change sizes was what? Okay, similarity transformation means you must do what?
Dilate.
Must dilate. Okay, you must dilate. All right? So that's what you need. Then similar figures. We know this already. 2 geometric figures are considered similar figures if and only if there is a similarity transformation that maps one onto the other. Again, I'm not going to get too wrapped up in definitions. You guys probably know similar figures by same what? Same shape. Different size. I'll turn that into a song someday. Same shape, different size. Oh, I love the similarities. That makes you wise. Or should I turn it into a rap?
Yes.
Yes.
Anything
You don't think my singing voice is musical worthy? Is that what you're telling me?
No, it's.
All right, that's okay. That's okay. I'll go cheer at the Twins baseball games. I can use my voice for that, right?
Yeah.
All right. I used it at the Hawkeye game the other night. That was a good one. Okay, we need to talk about some things. We have a toolbox for what, kids? What's that?
First clap out of spring training. Home run.
Who did?
First Bryant.
Yeah.
Yeah. He's on my
Kessler hit 2 the other day.
It's looking good.
All right. You have any Twins on your fantasy team?
Probably not.
I don't blame you. All right. Hey, all these original movements, call these coordinates x comma y, kids. Every one of these, x comma y, all the way down. Forgot to type them in. Okay, kids, we need to know or remember the transformations when we reflect points over x and y axis. I'm going to put a little sketch up over here. This is going to be a big time lifesaver for you, okay? Without going over these again, this could get kind of complicated. I want to make sure things are simple for you, okay? So let's visit. Up here, over here on the board, on the left. If I have a point, say maybe 3 comma 4 here, kids. So write 3 and up how much? Let's just pick on 3 comma 4. If I would reflect this over the x-axis, what coordinate would 3 comma 4 become by reflecting it over the x-axis? 3 comma negative 4. So the y value of positive 4 changes to what? So the transformation that takes place is xy becomes x comma what? Okay, we need to remember that. Okay? What if I would flip this over the y-axis over here? Then what would the coordinate be?
-3, 4.
Negative 3 comma 4. So what value changed?
-x.
So xy would map to what?
-xy.
Negative x comma y. Okay. Can I just give you the rules for rotation? Understand this. These rotations are under the assumption that they are going not clockwise, but counterclockwise. We're always rotations mathematically rotate in the order of which the quadrants go. 1, 2, 3, and 4. Okay? Here's how rotations work. All right? This would rotate over and then up this way, 90 degrees. But it would actually be left 4 and up 3. So a rotation of 90 degrees becomes the following, kids. It becomes the opposite of y, I think. Right's 3, run 4. Oh, hang on a second. Yeah, this would become, I got to think here. Hang on a second. I got 4. Yep. Negative y comma x is what this becomes. So kids, what would this point rotate to be if I rotated around the origin 90 degrees? What would 3 comma? Negative 4 comma 3. Okay. 180 degree rotation. Comes negative x, negative y. Okay. You see a pattern happening here? Switches, we'll move it to the front. Yep. Y, negative x. Okay. Do you have those rules down? Okay. That, I'm going to tell you what right now, that is going to save you a ton of headaches in this section right here to refer to it. Okay. And I'll show you why here in a little bit. All right. So first things first, do you have the toolbox for success filled out? Okay, I'm going to pick on a point. I'm going to pick on one point. Let's pick on the point 3 comma negative 5. Okay, raise your hand when you know this. 3 negative 5 is reflected over the x. What's the answer, Ty? 3, 5. 3 negative 5 is reflected over y. What is that, Leighton? Negative 3, negative 5. 90 degrees of rotation. This becomes 5 comma, careful. 5 comma x, right? Negative y comma x. So, okay. What's 180 degrees of rotation going to become? Negative 3, positive 5. What would 270 degrees of rotation become? Okay, understand how to read that? Okay, let's talk. Second page here, kids. So, I don't have a very good graph up here. It didn't work out well for me. So, I'm going to put a different graph up here. You guys can at least graph stuff up in that. So, give me a second here to pull a... hopefully, I can pull a coordinate plane into this thing. It says graph AB with which points?
A is 12.
Okay, 12, negative 6. And B is what?
0, negative 3.
0, negative 3. So what I need to do, kids, is get you the transformation. Here's what we're going to do to this, kids.
Of course, the graph only goes out.
Does it go to 12? I thought it went to 12.
I might not be able to. I can't look because it's like all blurry.
Yeah, that's a tough one, isn't it?
Maybe we need
Yeah, the
to.
graph only goes out.
All right, well, just go a little bit beyond. The rest will fit, okay? Okay, here's your idea, kids. You will, what I'm going to tell you is this. We don't really need to graph this. We will eventually, but what we want to do is reflect first in the, here are your movements that they're going to ask you to make. Reflection, kids. Is that a rigid motion?
Yeah.
Because it's not going to change the size. Reflect in the y-axis. That's the first movement we're going to make. And then the second movement we're going to make is dilate 1/3 x, I think. Yep. We're going to dilate 1/3. I'm going to dilate this way. I should put it this way. You can write the word dilate, but x comma y is going to become 1/3 x comma 1/3 y. So maybe without even graphing here, kids, maybe we can use that chart to come up with the new points for this figure in the end. Is that fair?
Yeah.
Okay, what's A's coordinate?
12
12, negative 6, and B is what?
0, negative.
Okay, so if we reflected A in the y-axis, kids, what would the first part of A become?
Negative 12, negative 6.
Okay, so we would flip the sign of the x value, right, according to our rules. So if I take 12, negative 6 and flip it over the y-axis, this is going to become negative 12, comma what? Well, negative 12, negative 6. What would B become, kids?
0, comma 8.
Yeah, it would become the opposite of 0, which is still what? So B prime would be 0, comma negative 3. So what we've done there, kids, the first thing we've done, wherever that line is, maybe you drew it, maybe you didn't. But we know enough about reflection stuff and what the coordinates are going to map into for its first image. Okay? Now they're saying, after you reflect over the y-axis, what am I really doing in that next one now? Yep. So here was 0, negative 3, and here was 12, negative 6 down here. There's a line that goes like this. And all we did is we flipped it over the y-axis. Now we're going to take that thing and are we going to enlarge it or reduce it? Why are you reducing it, kids?
It's less than 1.
Scale factor be less than 1. So where are my image points going to fall? I'll call this A double prime. Where does A double prime end up at? What's 1/3 of negative 12, in other words? Negative 4, and what's 1/3 of negative 6? Negative 2. So where is the final A, where's A going to rest at when we do all these moves? Negative 4, comma, negative 2. You tell me where B prime is going to lie. 0, comma, negative 1. Okay, so B double prime. So my question, kids, is this. Graphing or not graphing, can you perform a similarity transformation given the moves? You understand how to change the coordinates given a reflection into y? You understand what this means to dilate stuff? Once you have your new points, then multiply your x by what value? And then multiply your y by 1/3. If I would plot those points, is that segment going to be longer or shorter than the original one they had to start out with? It's going to be shorter because this was a dilation reduction. Good. Okay? All right. Let's check. Describing a similarity transformation. So up there it says, describe a similarity transformation that maps which trapezoid? Which trapezoid am I mapping to the other? WXYZ. Oh, okay. All right. WXYZ. This one, the big one, or the little one?
The little one.
Okay, so we're mapping from little to what? All right. Well, first of all, look at the orientation of these kids. Look at the orientation of the points. What kind of movement would you have to make with the smaller trapezoid compared to the bigger trapezoid? In other words, what do you have to do with the smaller trapezoid to make it kind of look like that first? 180 degree flip over the what? Okay, don't you agree that if I want to make this, I would have to flip this over the x-axis first? Yeah. These points would have to come up here, wouldn't they? Yeah. Okay? And I know you can't see this on the computer here, kids, but if I flipped it like this and made it look like this, doesn't that look like the same thing now? Yeah. Now, okay, so we have a reflection first where?
Over there.
Reflect in what? Reflect in x, right? Which means the points x comma y become x comma negative y. Okay? Then, kids, what's the second move?
Dilation more than one.
So dilate by, anybody know the scale factor? How'd you get 2? Good guess. It is correct. Okay, let me talk to you this way. How about this? Do you guys agree that when I flip this over, I'm actually going to draw this in here. Give me a second. When I flip W, X, Y, Z over the x-axis, this is kind of what it looks like in the end, right?
Well, it does double like each side one.
How about this side from W to Z right here? How is that related to this SP that's going to be? Yeah, so how many times bigger? If you take this, what's this length right here? What's this length? Okay, if you take the image length, or the one that we're mapping to, QRS, PQRS, 4, and divide it by the original length of 2, what is the scale factor? 2. Now, I want to check something here quickly, kids. I'm going to get rid of that. Oh, where'd my tools go? Hello, tools. Hey, there you are. Let me get rid of this. I want to check something. Guys, I'm going to look at the point Z. You guys got point Z?
Yeah.
If I take point Z and flipped it up and then dilated Z, where would Z actually fall at? Okay, let's just check this. We're going to check. We're going to check our point Z, which is what coordinate right now? 2 comma what? Oh, shoot, I ran out of paper. We're going to check this point Z. Z is the point 2 comma negative 1. Okay? Let's do the reflection in the X right now. What would 2 negative 1 become by reflecting it in the X? 2 comma 1. So a reflection in the X makes this become 2 comma 1. Now, dilate that puppy by a scale factor 2 from the origin, or where the origin is my center. 4 comma what?
2.
We said that by this description, Z should land on which point? What's the coordinate of S? So it looks like we've kind of done okay. Have we done okay?
That was easy.
This is not bad, is it? So they're going to show a couple of diagrams. Is that a transformation or a similarity transformation? What's the difference between transformation and similarity transformation?
Transformation, you must dilate.
A similarity transformation, you must do what?
Dilate.
Dilate. Is there dilating going on up there?
Yes.
You bet. Just a plain transformation is going to keep your size exactly the what? Okay, and we call transformations that keep the size or preserve the size what type of motions? Is that a rigid motion?
No.
No, because size did what? Done blow it up, didn't it? Okay, you guys feeling it right now? You buying what I'm selling?
Yeah.
Picking up what I'm laying down?
Yeah.
All right, let's move. Last example. Any questions so far? Okay, exciting stuff. We could probably do section 8.3 today too. I knew that was coming. All right, let's rock and roll, kids. Last example here in the notes. I don't like this example very much, but we're going to talk about it. Guys, you know that all squares are similar, right?
Yeah.
So our job is to prove that two squares are what up there? That they are similar, okay?
Why can't you
Lots
just
of different
say,
ways.
well, duh, it's a square.
Okay, here's the deal. It says prove that square ABCD is similar to what?
F-E-F-G-H.
Okay, so here's the deal. In order for something to be similar, it has to preserve angles, but lengths have to be different. But they have to be the same ratio. So here's what I'm going to do. Okay, when you talk about similarity, here's how I talk about this with kids. Okay, I'm going to make this as easy as possible. Instead of doing a two-column proof, can I just make this way easy for you?
Oh, yes.
Because I know two-column proofs are your favorite thing in the world to do, but you've done enough of those. Let's look at something maybe a little different in life. Is that fair? It's like eating M&Ms. You eat 14 green ones before you finally go, gosh dang it, I just want a red one.
They taste the same.
Huh?
Tastes the same.
Yeah, they do. Anyway, maybe I should have used Skittles as an analogy.
Yeah.
You eat 14 red ones before you finally say, gosh darn it, I want an orange one. Right? You've done so many two-column proofs, like, gosh dang it, can we prove this a little bit differently, right? Okay, so let's do it. Similarity. What do you know about similarity? Same what?
Same angles.
Same shape, which means I'm going to write this here. Angles are going to be what? Congruent. Okay. And then the next thing we need to do then, well, if it's the same shape, what's true about the size? Size can be different, right? But here's the deal. If one side of a shape is twice as long as another side, then every side should have the ratio of what to what? 1/2 or 2 to 1, depending on how you look at it, okay? So what we say about sides, kids, here is that the ratio of sides must be, here's the word, proportionate. Okay? What's given up there, kids?
Square ABCD. Wait, what? That's kind of a funky sentence.
It says square ABCD with side length S and square EFGH with side length 2S. And then AD is also what?
Parallel.
Parallel to EH. Doesn't make any difference what's parallel here. We got to prove that square ABCD is similar to what? Okay. Well, here's the deal. Angle A would match angle what here, kids?
E.
Because they're all going to be what kind of an angle? Angle E is congruent to angle E. Okay? But I've got to show that not just some angles are congruent. I need to show that all angles are congruent. And I can say that these are all going to be congruent because it's what kind of a shape? It's a square. And in a square, all interior angles are the what? Okay, so I don't really need to write that as a reason. So what would angle B match? Best friends, aren't they? How about angle C? What's that going to match? For the common good. Now, how about DH? Well, they only let those people play in the better league, the American League. Fleshner, you going to jump on me on that?
What?
Is the National League going to designated hitter pretty soon?
No.
Sounds like they're thinking about it. Oh, it would be way better. Have I shown all angles are congruent? Okay. Then we got to show ratio of sides. AD. Well, what is the sine of AD, kids? S. What's EH going to be? Okay, aren't all, and I'm not going to write them down. I'm going to do this. I'm going to say the ratio of AD to EH is the same as, let's see, let's go DC. DC would match what kids? So DC to HG. How many sides do I have to put here? What's BC going to match? And then one last one, AB to what? And these all equal, okay, what are the side lengths of all of these sides on a little square? S, or in other words, 1S over what? What's 1S over 2S going to simplify to? Okay. The ratio of all sides, the ratio of all corresponding sides is what value? 1/2. I've shown that the ratio of all sides is what? Means the ratio is exactly the same. That's what proportions are, equal ratios. Okay.
Area is 4 times bigger.
Area would be 4 times bigger. Okay. And we'll talk about that kind of stuff later. Okay. But guys, if they ask you to show that something is similar to another thing, you got to show that all the angles are what? And then all the sides must be proportionate there. Okay? Guys, in a nutshell, we're still talking about similarity. We're just taking things from similarity and things that we know about transformations and dilations, and we're putting it all together in a coordinate plane. So if I say here's a small shape and here's a big shape, can you describe how that small shape maps onto the big shape using either rotation, reflection, translation, or dilation, or a combination of those? Can you do that? Hopefully. Okay, I feel pretty confident that what we talked about, that you've got a pretty good grasp on right now. Okay? So questions about what's up there right now? That's my first one. Who needs time with that? Secondly.
Yes.
What? Nope, we should move on.
Okay, so thirdly, what I've got here, we've got about 15 minutes left here. I want you guys, I think I sent big ideas out, didn't I?
Yeah.
Okay, I'm going to go ahead and stop this. Give me a second.